Good morning, students. In previous class, that is class 5 of the first chapter, basic concept in chemistry, I already completed the 2 to 3 fundamental term. That is, what do you mean by percentage composition of an element? What is empirical formula and molecular formula? The relationship between empirical formula and molecular formula, and some problems relating to it. Let's recap to this again. That means first one, what do we mean by percentage composition? Percentage composition of an element is equal to the total mass of that individual element divided by the total mass of the molecule into 100. Basing upon this concept, 2 to 3 different ways are there, numericals are there. Case 1, first type of numerical, to calculate the individual percentage composition of an element. Second thing, we calculate the percentage composition of water of crystallization. Third case, we calculate the percentage composition of the cation or anion. Next is empirical formula and molecular formula. The actual formula of a molecule, molecular formula represent the actual formula, that means the actual number of each type of element present in a molecule. While the empirical formula gives the simplest ratio of each kind of element given in the formula. That means empirical formula into a whole number integer give rise to molecular formula. So basing upon that concept, while calculating the n, what is the formula for calculating n? N is equal to molecular formula by empirical formula. That ratio always maximum time is a whole number. If it is a fraction, then round up to nearest whole number. As a result, always that value of small n is a whole number. After knowing the small n, one is able to calculate the molecular formula. So before going to that, what are the steps are there? Step 1. First we calculate the empirical formula. How we calculate the empirical formula? By forming a box. That means 5 to 6 column is there. Column 1, that is a type of element. Column 2, that is the percentage. Column 3, that is the atomic masses. Column 4, that is the atomic ratio. How we calculate atomic ratio? That is percentage divided by atomic mass. Then we calculate the simplest ratio. Then we calculate the simplest whole number ratio. So in this way, from this box, one is able to calculate the empirical formula. Then one is calculate the empirical formula mass. Then one calculate molecular formula mass. Molecular formula direct given in the question, or vapor density is given. One formula is there, that is molecular mass is equal to 2 into vapor density. In this way, molecular formula mass is calculated. So, dividing molecular formula mass by empirical formula mass, one is calculate the value of small n. After knowing the value of small n, empirical formula into that small n give rise to the molecular formula. Today, in class 6 of the chapter Basic Concept in Chemistry, I will try to cover another one term, that is stoichiometry. Mark that. What do you mean by the term stoichiometry? The stoichiometry derived from the Greek word, mark that, stoichio. It means element, and another word is meterin, means measure. So, in this problem, in this heading, that is in the stoichiometry, we calculate some problems relating to chemical reaction. That means if we compare this one, stoichiometry is nothing but the calculation of relative amount. That means it means calculation of relative amount of substances relative amount of substances in a chemical reaction. In a chemical reaction is known as stoichiometry. So under this heading, we go through generally three types of problem. One is mass-mass relationship, problem based upon mass-mass relationship, problem based upon mass-volume relationship, and third one, problem based upon volume-volume relationship. Mark that. Under this heading, we solve generally three types of problem. That is, point one, problem based upon mass relationship. Point two, problems based upon mass volume relationship, and third one is problems based upon volume relationship. Mark that. Normally, we cover three types of problem. One is problem based upon mass relationship. Under this heading, the problem based upon the mass relationship, one of the reactant, we have to calculate one of the mass of one of the reactant and a product simultaneously. If mass of one of the reactant and product is given, I repeat again, under this heading, we have to calculate the mass of any one of the reactant and product. Condition is that mass of any one of the reactant and product is given. Point two, under this heading, we have to calculate the mass or volume of any one of the reactant and product. Condition is that mass or volume of any one of the reactant and product also given. And point three, problem based upon volume relationship. Under this heading, we have to calculate the volume of any one of the reactant and product. Condition is that volume of any one of the reactant product also given. So let us apply. First, we go through the problem based upon mass relationship. Mark the question. What is the data given? How much potassium chloride is needed to produce enough oxygen for the burning of 10 gram of coke? So we solve this problem on the basis upon two steps. First one is burning of 10 gram of coke. Mark the equation. Answer. The required equation, for burning of coke, the required expression for burning of coke means C plus O2 give rise to CO2. Carbon, coke means carbon, C plus O2 give rise to CO2. That means it is 1 mole, it is 1 mole, and it is 1 mole. 1 mole of carbon equivalent to 12 gram, 1 mole of oxygen equivalent to 32 gram. So from this expression it is clear that, from the above data it is clear that 12 gram of carbon are required for complete oxygen, 32 gram of oxygen. Mark that. From the above data, it is clear that for the complete combustion of 12 gram of coke. From the above data it is clear that from the complete combustion of 12 gram of coke, 32 gram of oxygen is required. Mark that. From the data it is clear that from the complete combustion of 12 gram of coke, from the burning of 12 gram of coke, how much? That means 32 gram of oxygen is required. By the question, burning of 10 gram of coke. Therefore, by the burning of 10 gram of coke, oxygen required equivalent to, how you solve this one? That means for 32 gram, for burning of 12 gram, 32 is required. For 1 gram, for 10 gram. Mark. Is equal to 32 by 12 into 10. Mark, I repeat again. For burning of 12 gram of coke, oxygen required 32 gram. For burning 1 gram of coke, 32 by 12. For burning 10 gram of coke, 32 by 12 into 10, nearly equal to 26.6 gram of oxygen. So bit one is over. Next, we write the required expression for decomposition of potassium chloride to liberate oxygen. Next we find out. Next we represent one equation for liberating oxygen for potassium chloride. Next, that means the required equation, the required chemical equation representing decomposition of potassium chloride to liberate oxygen is, that is KClO3 breakdown to KCl plus O2. Mark that potassium chloride on decomposed to give potassium chloride and oxygen. From this it is clear that it is 2 mole and oxygen is equal to 3 mole. That means 2 is equal to 2 into, it is 39 plus 35.5, 3 into 16. That means on solving, this value nearly equal to 245 gram. Then it is 3 mole, 3 into 2 into 16. Mass of one oxygen is 16. So 2 is there. On solving, this one nearly equal to 96 gram. That means on decomposition of 245 gram of potassium chloride liberate 96 gram of oxygen. Then 96 gram of oxygen liberated from 245 gram of potassium chloride, 1 gram of oxygen liberated from the end question is 26.6 gram of oxygen liberated from what fraction of potassium chloride? Are there? That means we write (96 gram of oxygen is liberated from 245 gram of potassium chloride. Therefore, 26.6 gram of oxygen is liberated from is equivalent to 245 divided by 96 into 26.6. 245 by 96 into 26.6 nearly equal to 68 gram. That means for the complete combustion of, that means how much quantity of how many gram of oxygen is required? That means 68 gram of oxygen is evolved from the decomposition of burning of, that means 245 gram of potassium chloride. Next, move to another type of problem. Mark the second question. What is the question? How many gram of calcium carbonate is heated to get enough carbon dioxide which can convert 0.1 mole of sodium carbonate into sodium bicarbonate? This problem also based upon two phases. Mark that. First one, mark that is decomposition of calcium carbonate to find out how many amount of carbon dioxide is involved. Mark the answer. The required expression for the decomposition of calcium carbonate is, that is calcium carbonate on breakdown to calcium oxide plus carbon dioxide. It is 1 mole. It is 1 mole. That is 1 mole means 40 plus 12 plus 48 equivalent to 100 gram. 1 mole of carbon dioxide means 44 gram. Mark that. On the decomposition of 100 gram of calcium carbonate, 44 gram of carbon dioxide is evolved. I repeat again. That means it is one equation, then move to the another equation which can convert sodium carbonate to sodium bicarbonate. Next, the required expression for conversion of sodium carbonate Na2CO3 to sodium bicarbonate NaCO3. That means Na2CO3 plus CO2 plus H2O give rise to NaHCO3. Mark the equation. Sodium carbonate combined with carbon dioxide plus water to give sodium bicarbonate. That means it is 1 mole. It is 1 mole. 1 mole of sodium carbonate, if we add, that is 2 into 23 plus 12 plus 48, 106 gram. 106 gram of carbon dioxide, required carbon dioxide is 44 gram. So mark that from this equation 1 it is clear that 1 mole of carbon dioxide is produced. 1 mole of carbon dioxide is produced from equation 1, and same 1 mole of carbon dioxide is consumed in equation 2. Now 1 mole of sodium carbonate will be required. 1 mole of sodium carbonate required. 1 mole of carbon dioxide. So 0.1 mole of sodium carbonate required, 0.1 mole of sodium carbon dioxide. I repeat again. From these two equations it is clear that for the decomposition of calcium carbonate 1 mole is involved. That 1 mole is involved required. That means in conversion of sodium carbonate to sodium bicarbonate. So in the question 0.1 mole of sodium carbonate converted to sodium bicarbonate. So for the conversion of 0.1 mole of sodium carbonate to sodium bicarbonate, 0.1 mole of carbon dioxide is utilized. So from this equation it is clear that 1 mole of carbon dioxide, that is 1 mole of carbon dioxide is evolved from 1 mole of calcium carbonate. That means 44 gram of carbon dioxide evolved from 100 gram of calcium carbonate. So question is 0.1 mole. If 1 mole is 44, 1 mole is required at 100 gram, then 0.1 mole required 100 by 10 equivalent to 10 gram. Mark the expression. If 1 mole of carbon dioxide required for conversion of sodium carbonate to sodium bicarbonate, and my question 0.1 mole of conversion of sodium carbonate to sodium bicarbonate, 0.1 mole of CO2 is required. Mark that. 0.1 mole of carbon dioxide That means 1 mole of calcium carbonate equivalent to 100 gram. That means 0.1 mole of calcium carbonate required. Its value is equal to 100 by 10 is equal to 10 gram. That means 10 gram of calcium carbonate is needed to get enough carbon dioxide which can convert 0.1 mole of sodium carbonate to sodium bicarbonate. It is little idea about the phase 1 problem, that is problem based upon mass relationship. Now transfer to phase 2, that is problem based upon mass volume relationship. Mark that next question. What is the next question? Mark that. What volume of carbon dioxide gas at NTP can be obtained from 2 kg of calcium carbonate? Again, what volume of carbon dioxide gas at NTP obtained from 2 kg of calcium carbonate? One thing is the important thing. While solving this one, we have to remember one thing. For every gases, the volume at NTP, that means the GMM, gram molecular mass, equivalent to gram molecular volume. So at NTP, gram molecular volume always 22.4 liter for 1 mole of any gas. So come to the point, the required expression, mark that. The required expression for the decomposition of calcium carbonate is CaCO3 breakdown to calcium oxide plus carbon dioxide. So here it is 1 mole. It is 1 mole. That is equal to 40 plus 12 plus 48. 100 gram. It is 44 gram. That means 1 mole equivalent to, if we transfer to volume, is equal to 22.4 liter at NTP. From this it is clear that, mark that, from this expression it is clear that 100 gram of calcium carbonate liberated 22.4 liter of carbon dioxide. If 100 gram of calcium carbonate liberated this amount of volume, then according to question, what? 2 kg of calcium carbonate. Therefore, the total volume of CO2 gas liberated at NTP from 2 kg of calcium carbonate equivalent to 22.4 divided by 100 into 2 kg means 2000 gram. On solving this one, the value is 448 liter. So, what volume of carbon dioxide gas will be obtained? 448 liter of carbon dioxide gas is obtained by the decomposition of 2 kg of calcium carbonate. Move to another type of problem. Mark the next problem. What is the next problem? Next problem is 112 gram of pure iron are completely converted into ferric chloride and dissolved in water. How many liter of hydrogen sulfide gas at NTP will be required to convert this entire amount of ferric chloride to ferrous chloride? Mark that. The question is, this question indicates that two required expression is there. First required expression is iron combines with chlorine to form ferric chloride. Second expression is ferric chloride transferred to ferrous chloride. Let us observe that answer. The required expression for the formation of ferric chloride is iron combines with chlorine to form ferric chloride. That means 2, 3, 2. So it is clear that 2 moles of iron combines with 3 moles of chlorine to form ferric chloride. That means if we mark the mass, that is 2 into 56, 112 gram. Equivalent to, if we discuss about ferric chloride, that is 2 whole into 56 plus 3 into 35.5. If you multiply this one, the exact value is 325 gram. So mark that 12 gram of iron when converted to ferric chloride, it forms 325 gram ferric chloride. It is about the first equation. Then switch over to the second expression. What is the second expression? Second expression is the conversion of ferric chloride to ferrous chloride. Mark the second expression. That is conversion of ferric chloride to ferrous chloride. The required expression for the conversion of ferric chloride to ferrous chloride is given by that means FeCl3 plus HCl. Ferric chloride combines with hydrogen chloride to form ferrous chloride plus hydrogen chloride plus sulfur. Equivalence, multiply 2 here. Equivalence, the combines with hydrogen sulfide. Equivalence 2 ferric chloride, it is 2 ferrous chloride plus 2 HCl. So from this expression it is clear that it is 2 mole and it is 1 mole. That means 2 mole of ferric chloride required 1 mole of hydrogen sulfide to transfer to ferrous chloride. We calculate that is 325 gram. So 3D is equivalent to 325 gram of ferric chloride required 1 mole means 22.4 liter. That means 22.4 liter of hydrogen sulfide gas at NTP will be required for the converting this total amount of ferric chloride into ferrous chloride. It is the little idea about the second type of problem, that is relationship between mass and volume. Then move to third type of problem, that is relationship between volume and volume. Mark the next problem. What is the next problem? Calculate the volume of oxygen necessary to burn completely 5 liter of butane gas, and also calculate the volume of carbon dioxide liberated. Mark that it is volume relationship. Equal concept is that equal volume of all gases contain equal number of molecules. So mark that. So first we have to calculate the required expression for combustion of butane. Answer. The required expression for the combustion of butane is C4H10 plus O2 give rise to CO2 plus H2O. So mark that is the required expression for combustion of butane. On balancing it by the heat and trial method, then it is 2 mole of butane, 30 mole of oxygen give rise to 8 and 10. That is, it is 2 volume, 13 volume, 8 volume, or it is 2 liter, 13 liter, then 8 liter. Then according to question, 5 liter of butane. Therefore, 5 liter of butane produce what amount of oxygen and also produce what amount of carbon dioxide. Mark that. 2 liter of butane required 13 liter of oxygen. Then what volume of oxygen required for 5 liter of butane? If 2 liter of butane required 30 liter of oxygen, then 5 liter of butane required. Mark that. That means, mark the equation. 2 liter of butane required 13 liter of O2. Therefore, 5 liter of butane required equal to 13 by 2 into 5. Mark that. 13 by 2 into 5. On solving this one, this is equal to 32.5 liter. 32.5 liter. Move to second one is, that means 2 liter of butane produce 8 liter of carbon dioxide. Mark that. Again 2 liter of butane produces 8 liter of carbon dioxide. Therefore, 5 liter of butane produces equivalent to, that means 8 by 2 into 5, that means equal to 20 liter of carbon dioxide. So question is, calculate the volume of oxygen necessary. 32.5 liter of oxygen necessary for bond completely 5 liter of butane, and also calculate the volume, the 20 liter of carbon dioxide also for by the burning completely of 5 liter of butane. Move to another type of problem relating to volume relationship. Mark the second question. What is the second question? In the Austral process for the manufacture of nitric acid, ammonia gas is burned completely in oxygen in presence of a platinum catalyst. What volume of oxygen is required and what volume of nitric oxide is for in the combustion of 500 liter of ammonia during Austral process for the manufacture of nitric oxide. So solve that. It is important thing is that we have to write a balanced equation for combustion of ammonia for formation of nitric oxide. Mark that answer. The required expression is given as that is NH3 plus O2 give rise to NO plus water. Ammonia when undergoes combustion give rise to nitric oxide and water in presence of catalyst platinum. On solving, it is 4 molecule of ammonia combined with 5 mole of oxygen to for 4 mole of nitric oxide and 6 mole of water. That is, it is 4 volume, it is 5 volume, it is 4 volume, or it is 4 liter, it is 5 liter, it is 4 liter. Question, if it is 500 liter, we have to find out what is the value of oxygen required and what is the value of nitric oxide required. Mark the equation. Mark. So from this equation it is clear that 4 liter of ammonia required, 5 liter of oxygen. Therefore, 500 liter of ammonia required. 5 by 4 into 500. On solving this one, it will equal to 625 liter of oxygen. That means for the combustion of 500 more liter of ammonia, the volume of oxygen required is 625 liter. Again, from this expression it is clear that on combustion of 4 liter of ammonia, 4 liter of nitric oxide is formed. So by the process on combustion of 5 liter of ammonia, the amount of nitric oxide liberated must be equal to the 500 ml. That means what is the statement? Mark that. From the expression, from the equation, it is clear that 4 liters of ammonia will liberate 4 liters of NO, nitric oxide. Therefore 500 liters of ammonia produces 500 liters of ammonia produces, that is 500 liters of nitric oxide. These are some problems based upon mass relationship, mass volume relationship, and volume relationship.